Hello, this is Jeff Bowen here with a review of the distance formula. So, let's get started. We're going to actually define the distance formula today, and we're going to come to a natural conclusion about how it arises. Alright, so I'm not even going to write down the distance formula here. Instead, I'm going to write down something else that's going to be used to derive the distance formula so that we can understand where it comes from. And for that, we're going to need two things. This is going to be a union between geometry and a union between algebra. All right. And specifically with algebra, we're going to be taking a look at the Cartesian coordinate plane. Okay. So, from the geometry side of things, one thing that we're going to be proving very soon in our geometry section that we're working towards with our study of Euclid's elements is one of the big formulas of all of mathematics, one of what I think is one of the most important formulas, and that being the Pythagorean Theorem, which is, of course, a squared plus b squared equals c squared when we have a triangle that is a right triangle, meaning that one of its angles is 90 degrees, such that this is A, this is B, and this hypotenuse here, this longest side of the triangle opposite this 90 degrees, is always C. I'm going to spend some time going over a few ways to come to this Pythagorean theorem, but for now we're going to use it to help us understand this distance formula. Okay? So let's go over here to the algebra side of things. Let's give ourselves a Cartesian coordinate plane. And let's just mark off some spots on the coordinate plane. Okay? You could say we have a function, maybe y equals x, y equals 2x. We're not even going to go that far. All we're going to actually say is we have some points. Let's see, how about the point 1, 2? So this is the point right here, 1, 2. And how about the point 4, 4 up here? All right, I can see some people are probably getting excited out there. You want to actually go ahead, you want to connect these two together, find the slope, find the line that defines these 2 points. We're actually not concerned with that at the moment, although that is a related task that you could undertake. What we're actually concerned about in this particular circumstance is the distance from this point here to this point here. All right, we want to know what the distance between these 2 points is. And one of the base ideas of Euclidean geometry in two-dimensional planes is that the shortest distance between 2 areas is usually a straight line, right? Let's say that you want to go to Sonny's. All right, Sonny's is a nice pizza shop in town. I like it myself. Well, the quickest way to get to Sonny's would be to travel straight there. I mean, if you could go through buildings, if you could go through brick walls, if you could just zoom straight there from your current spot, that would define the shortest distance between you and your destination, all right? A straight line between those 2 areas. But what is this? How would we find out what this distance actually is? All right, there's obviously some application for this beyond going to the pizza place. If you want to find the shortest distance between 2 areas in a relatively Euclidean, and what I mean by that in a small area, then you would want some sort of formula to help you out. Well, let's take a look at this for a second. All right, this spot here, 1, 2, and this spot here, 4, 4. What should we do? Take a moment, think about it. There's actually a really good way. I just don't want to give it away right away, so I'm going to give you 5 seconds. You can pause the video, take a look at this, figure out what the distance from here to here is, knowing that we're going to be using this somehow And this is all we have. All right, so hopefully you've taken a moment, you've thought about it, you paused the video. Here we go. All right. Well, this line here, imagine for a second that we actually did have a right triangle. Okay? All right? And that this here, this distance that we're actually trying to find would be the hypotenuse of a right triangle. Then what would you need in order to determine what this is? Well, you would need the distance from this point to here, this other point that we haven't actually defined yet, and you would need the distance from this other point we haven't defined yet going up. So you would need this, and you would need this. But here's the great thing about our Cartesian coordinate plane right now. This line is a horizontal one that is, parallel to the x-axis, meaning that wouldn't the distance from here to here be the difference between this number, which defines our x value for this spot here, which is 1, and the x value here, which is 4. Or if you prefer, you could just count 1, 2, 3. The distance from here to here is 3, or it's 4 minus 1, which is 3. And again, we could just count for this change in vertical nature from here to here. Well, let's see, we're starting at 2, 1, 2. All right, so the distance here is 2. Or you could think of that as 4 minus 2 is 2. Okay, good. So now we have a right triangle with an unknown hypotenuse. We can use our Pythagorean theorem to solve this because look, let's just map this over. B is 2. A is 3. Let's plug it in. Let's plug it into our equation. 3 squared plus 2 squared equals c squared. All right. 3 squared is 9. 2 squared is 4. Still equals c squared. This over here, 9 plus 4 is 13, which is still equal to c squared. Now this is the part where some people get a little confused. 13 is equal to c squared, all right? That doesn't mean that 13 squared is 169. That's not what we're getting at here. In fact, what we're saying is that the square root, in order to undo the inverse operation of squaring for this c, is taking the square root of both sides of the equation, which cancels out that squaring, meaning that c is actually equal to the square root of 13, which is an irrational number, but that's okay. So many numbers are irrational. And thus we have found that the distance from this point here to this point here is the square root of 13. Now, because that's an irrational number, you might say that you're not sure about that. Well, you can get out your calculator. You can take the actual square root of 13 and find out what that is. And you'll find out that it's approximately 3.6. All right, square root of 13 is approximately 3.6. And now maybe that answer makes a little more sense to you. I mean, you have a 3 here, a 2 here, and the distance between here and here, well, it's longer because it's the longest part of this triangle. It's approximately 3.6. So let's spend a moment and let's define the distance formula. All right. Let's take a look at what we did and use some more generalized terms. Instead of using numbers, let's find an actual formula so that when we have whatever numbers we might have, we can just plug those numbers in and find our distance. All right, so what did we do before? Well, I said we could have counted here, but another way to determine what this x value was, or what this distance here was, excuse me, I mean to say distance, not x value. What the distance here on it was 4 minus 1. 4 minus 1. All right, that's how we got 3. That we then plug the 3 in up here. Okay? So bear with me for a second. 4 minus 1 became 3. And how did we find the other value? Oh, that was 4 minus 2. Okay. Now, that became 2. This was 3 squared. This was 2 squared, and we added them together. And that was equal to c squared. All right, our final answer. Well, let's take this, and let's put this in parentheses and move that square up here. I mean, 3 squared was really just 4 minus 1 squared, right? Take a moment, convince yourself of that. And 2 squared, really that was just 4 minus 2, then squared, okay? Good so far? Well, we added those together, and we got out c squared. Okay? Now, we took the square root of both sides of the equation, so let's take the entire square root of everything over here so that we can cancel this out. So now all we have left on this side is c. Starting to look familiar? Just another second and we'll have it. All right. Instead of calling, well, this was our second x coordinate, okay? On this plane it was the second x coordinate. Let's call that x sub 2 for the second x coordinate in our plane. Likewise, this was the first x coordinate in our plane. So let's call that x sub 1. Over here, this 4 here, that was the second y coordinate. Let's call that y sub 2. And this 2 here, that was our first y coordinate. All right. One more altercation, very minor. We wanted to find the distance from here to here. Well, instead of calling that c, let's call it d for distance. And there you have it. That's the distance formula. The distance between 2 points is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. We found that by taking a look at the Pythagorean Theorem and mixing it with some algebra, mixing it with our Cartesian coordinate plane. All right. Go forward, use this formula in whatever way helps you through your life. If not just for the pure love of mathematics, maybe something a little more rigid and necessary, but it's up to you. It's all fun, right? Have a great day. This is Jeff Bowen signing off.